Now that we understand spherical coordinates, the definition of spherical coordinates, we want to compute the Jacobian of the transformation. This is the transformation that we derived in the last video, the formulas for the x, y, and z coordinates with respect to rho, phi, and theta, the different angles. Because, again, of course, if we're going to integrate anything in spherical coordinates, we're going to have to know how the volume element changes. And so remember that the volume element in our spherical coordinates is going to equal, so the better way to say it is the volume element in the xyz coordinates is going to equal the Jacobian of this transformation, rho phi theta, times the volume element in this rho phi theta sense. And so in other words, dx, dy, dz, usual tiny rectangular volume element is going to be equal to Jacobian, rho phi theta. Those are the variables that we want to have in here, times d rho, d phi, d theta, right? And so, of course, the question is, what does this Jacobian equal? And, well, let's compute it. So there's a way to compute it. But before we do, let's think about what a tiny volume element would look like. And so if we're going to chop up a solid sphere, a solid spherical region, into pieces, we might think of a couple concentric spheres. And we might think of a couple rays coming from the origin, so that cut right through our space here. And so what we'll end up with is that a small portion of the volume here looks kind of like a projected curved portion of a rind of maybe a watermelon or something that has this curvature. The piece is a little bit bigger on the top than on the bottom, and in between it's all solid, right? And so the question of what does the Jacobian measure is it measures how the volume of this thing is compared to the volume of just a rectangular, a purely rectangular prism here, as opposed to this spherical prism, essentially, that we've built here. So the Jacobian is going to measure the volume of this tiny piece here. And there is a geometric argument that you could use, that you could provide here, to compute the volume of this piece. But since we know how to take the Jacobian, it's going to be a lot easier for us to just compute. So let's do it. So remember the Jacobian of a three-dimensional transformation. Let's start with the Jacobian matrix. The Jacobian matrix is going to be the matrix of partial derivatives. So go back and review this definition. I'm not going to write out all the symbols, but what we have to do is systematically take the derivatives of x, y, and z with respect to rho, phi, and theta, and we have to go in the order that we've prescribed, rho, phi, theta. If you go back to the last lecture video, we decided that rho, then phi, then theta was the correct direction to go. So we take the derivatives of all of these component functions here with respect to rho first. Rho shows up in all of them, right? And the derivative with respect to rho is just going to eliminate it from each one. So the first column here is sine of phi, cosine of theta, then sine of phi, sine of theta, and then just cosine of phi. All right. The next column of our Jacobian matrix, we need to take the derivative of these functions with respect to phi. Derivative of sine is cosine, cosine is minus sine, so this ends up being rho, cosine of phi, cosine of theta, rho, cosine of phi, sine of theta, and then minus rho, sine of phi. And then in the third column, we put the derivatives of all of these functions individually with respect to theta. There are no thetas for the z component, so that one's going to be 0. That'll be nice. And then each of these are just cosine sine, so this one's going to be minus rho, sine of phi, sine of theta, and this one will be positive rho, sine of phi, cosine of theta. So this is our Jacobian matrix, and now the Jacobian function is the determinant of this matrix. Okay, and so there are different ways to compute the Jacobian. One way is to systematically, so to pick maybe a row or a column so pick a row or a column that has a 0 for sure. Maybe that's not even the best one to pick. Let's pick this bottom row. So pick the bottom row. We're going to expand on this, and because it has a 0, it's going to zero out some stuff for us. Now, when you do the Jacobian by this method, this is the kind of the linear algebra approach using adjoint matrices, you have to very carefully figure out what the signs of the Jacobian are going to be. So this first term is a plus, and this second term we have to subtract off. But if we write this out, the way that this works is when we get to the cosine term, so this cosine of phi, what do? We multiply this cosine of phi by the determinant of the resulting 2 by 2 matrix that we would get by crossing off the row and the column that cosine phi lives in. So now we take the crisscross determinant product of this, and we see that we get, this product is going to be rho squared cosine phi sine phi times cosine squared theta minus a negative, so plus rho squared cosine phi sine phi times sine squared theta. Okay, so that's this one. And then we go to the next one. So I'm going to just stack, we have to add this up, right? So the next one's going to be plus. We have a minus, minus, so those will cancel. And so here we get our rho sine of phi on the outside. And for this one, what we have to do is take the determinant of the matrix that we get by crossing off the middle row and doing our crisscross determinant product on these two. So this one's going to be sine of phi, sine squared phi, cosine squared phi times rho. So this is rho sine squared phi, cosine squared theta, cosine squared theta, minus a negative again, so plus rho sine squared phi, sine squared theta. Okay? And then, of course, because of the choice of using the third row to expand on, we've got a 0 here, and so that's going to just contribute 0 to the Jacobian. Now what we have to do is add these two up, but we're going to take advantage of the structure here. And so we notice that in the first one, we have cosine squared, sine squared, and then the thing multiplied by it is the same, right? So by Pythagorean identity, this whole term is just... So this whole term is cosine of phi is still there, times the single rho squared cosine phi sine phi. And similar things happen on the next one. So on this one we have rho sine squared phi on each term, and what factors out is Pythagorean identity. Again, here's rho, and so we've got rho sine of phi times rho sine squared phi. All right, and then again we want to simplify this, and we start to see some more Pythagorean identities here. So I'm going to write everything out, but I'm going to be very careful. We've got a sine phi here, a sine phi here, rho squared here, rho squared here. There's two rows here. So what I'm actually going to do is factor out rho squared times sine of phi. That's what's common to each of these. And when I do that, so rho squared sine of phi, rho squared sine of phi. What's left is cosine squared phi plus sine squared phi. And that is another Pythagorean identity. So this term is just 1. And what we get after this is, you know, a little bit, you have to be careful as you work through this, but it's not really that difficult. It's mostly just making sure you're keeping everything straight and noticing these Pythagorean identities. What we get is that the Jacobian of the spherical transformation is rho squared times sine of phi. Okay? And so that means that our volume element, or dV, for spherical coordinates is going to be rho squared sine of phi d rho d phi d theta.